In the ever expanding horizon of educational innovation, artificial intelligence emerges as the next frontier. This is your Professor Atif Fareed Muhammad. We'll be looking at that from where we left off as our last lecture on AI, the next frontier, promising to redefine the predictive capabilities within the university systems as our use case today going to be. I'll follow the Edmund Husserl's example, who was the author of Logical Investigations and a mathematician, the founding father of phenomenology as well, would likely approach this topic with a deep philosophical inquiry if Edmund Husserl does that. So we can explore the essence of AI's role in shaping the educational experience on the basis of logical investigations, even. By delving into the phenomenological layers of AI integration, we uncover a transformative potential that transcends mere operational efficiency. Predictive AI models, when applied to student data, reveal intricate patterns of behavior and performance, offering a holistic understanding of the student journey. This phenomenological lens allows educators to perceive the student not just as a data point but as complex individual with unique needs and potential. We'll be looking at predictive modeling, clustering, recommendation engine, and specific on the basis of predictive modeling and clustering. As Edmund Husserl's emphasis on intentionality and lived experience would guide us to consider the ethical and existential implications of AI in education. So I'll be using phenomenology, which is the work that Edmund Husserl and later his disciple Martin Heidegger did. We'll look into that together in the light of those two pillars in the educational leadership or in the mathematics domain. The predictive use of AI must be grounded in a profound respect for the students' autonomy and the integrity of their educational journey. It is essential to ensure that AI systems are designed with transparency and fairness, avoiding the pitfalls of algorithmic bias. By embracing a phenomenological approach, universities can harness AI to create a more empathetic and responsive educational environment. This philosophical underpinning ensures that the integration of AI is not merely a technological upgrade, but a thoughtful evolution that enhances the human experiences of learning and growth. In this way, AI becomes a tool for deepening our understanding of the educational process, aligning with Edmund Husserl's vision of a world where technology serves to enrich rather than diminish our humanity. Predictive modeling. In the sweeping arc of human history, predictive modeling emerges as a transformative force, set to revolutionize the very essence of university systems. This technological leap stands alongside the agriculture and industrial revolutions as a turning point in our societal evolution. By leveraging predictive algorithms, universities can foresee student needs, streamline resource allocation, and craft personalized learning journeys that honor the unique attributes of each individual. This shift is not merely about enhancing efficiency, it is about reimagining education in a way that aligns with the digital age. The integration of predictive modeling allowing universities to transition from reactive to proactive strategies, identifying students at risk of falling behind and implementing targeted interventions to ensure their success. This capability not only elevates academic outcomes but also cultivates a more inclusive and supportive educational environment. However, it is essential to approach this technological advancement with caution, ensuring that ethical considerations and human oversight are at the forefront. The use of predictive modeling must be guided by a commitment to equity and transparency, ensuring that these tools serve to empower rather the marginalized students population. So this also helps in making the informed decisions, optimizing resources, and improving outcomes. University system use case, as I started, the components are admissions, enrollment, academic performance, student retention, financial aid, alumni engagement. As we stand at the precipice of this new era of artificial intelligence, it is vital to acknowledge that transformative potential of predictive modeling while remaining mindful of its ethical and social implications. A balanced approach where technology complements but does not supplant human judgment is crucial. By embracing predictive modeling with the discerning and thoughtful perspective, universities can navigate the intricacies of the data driven future, creating educational experiences that are both innovative and deeply humane. In doing so, the integration of predictive modeling in university systems become more not just a technological milestone, but a significant step forward in our collective journey towards a more enlightened and equitable society. Again, the university system use case has data sources like student records, academic performance data, financial aid information, and survey responses. Let's look into these with few more in-depth detailed discussion. The student admissions can use predictive modeling for predicting enrollment rates, academic performance identifying at-risk students, student retention predicting dropout rates, financial aid optimizing aid distribution, alumni engagement predicting donor behavior. So these are some of the areas where predictive modeling can be very helpful. Data collection and preparation. Data types are structured databases and unstructured text and images. Data cleaning should be happening earlier, handling missing values, outliers, and inconsistencies. Transformation, normalization, and encoding categorical variables are needed. Data collection is the cornerstone of any successful AI predictive modeling initiative within a university system. To harness the power of AI, universities must first gather comprehensive and relevant data from various sources. This includes academic records, student demographics, engagement metrics, financial aid information, and even external data such as economic indicators and social trends. By casting a wide net, universities can build a rich dataset that captures the multifaceted nature of the educational experience. This holistic approach ensures that the predictive models are fed with diverse and meaningful data, laying the groundwork for accurate and insightful predictions. Once the data is collected, the next critical step is data preparation. Raw data is often messy, incomplete, and inconsistent, requiring meticulous cleaning and pre-processing. This involves handling missing values, removing duplicates, and correcting errors. Data normalization and standardization are also essential to ensure that all variables are on a comparable scale, which is crucial for the effectiveness of predictive models. Additionally, feature engineering plays a pivotal role in transforming raw data into meaningful inputs. This process involves creating new features that capture underlying patterns and relationships, enhancing the model's ability to make accurate predictions. Data integration is another crucial aspect of preparation. Universities often have data siloed in different departments and systems, such as admissions, academic affairs, and student services. Integrating these disparate data sources into a unified dataset allows for a more comprehensive view of students' behaviors and outcomes. This integrated approach enables predictive models to identify complex interactions and dependencies that would otherwise go unnoticed. For example, combining academic performance data with engagement metrics can reveal how extracurricular activities influence student success, providing valuable insights for targeted interventions. Let me emphasize on the fact that ethical considerations are paramount in data collection and preparation. Universities must ensure that data is collected and used in a manner that respects students' privacy and complies with data protection regulations, as well as the compilation that happens remains within the university's boundaries. This includes obtaining informed consent, anonymizing data where necessary, and implementing robust security measures to protect sensitive information. Additionally, it is crucial to address potential biases in the data that could lead to unfair and discriminatory outcomes. By prioritizing ethical data practices, universities can build trust with students and stakeholders, ensuring that the benefit of AI predictive modeling are realized in a fair and equitable manner. Continuous monitoring and updating the data are essential for long-term success of AI predictive modeling. This educational landscape is dynamic, with changing student populations, evolving curricula, and shifting external factors. Regularly updating the dataset with new information ensures that the predictive models remain relevant and accurate. This ongoing process of data collection, preparation, and integration allows universities to update to new challenges and opportunities, continuously improving the educational experience for students. By embracing the data driven approach, universities can leverage AI predictive modeling to create a more personalized, efficient, and effective educational system that benefits both the institutions and its students. The predictive modeling techniques here are few: regression analysis, linear or logistic regression. Machine learning is decision trees, random forests, neural networks. Time series analysis has ARIMA or SARIMA. It looks like names. Clustering are k-means, hierarchical clustering, and let's look into this with one example use case within the university system on each of these. Linear regression analysis is a fundamental statistical technique that plays a crucial role in enhancing university systems by predicting and understanding key outcomes. At its core, linear regression establishes a relationship between dependent variable, the outcome of interest, and one or more independent variables or predictors. For instance, a university might use linear regression to predict students' GPAs based on factors such as hours spent studying, attendance records, and participation in extracurricular activities. By quantifying these relationships, universities can gain valuable insights into what drives student success, enabling them to make data-driven decisions that improve academic performance and overall student satisfaction. One of the primary benefits of linear regression in a university setting is its ability to identify significant predictors of students' outcomes. By analyzing historical data, universities can determine which factors have the most substantial impact on student achievement. For example, linear regression might reveal that attendance is a stronger predictor of GPA than hours spent studying. Armed with this knowledge, universities can allocate resources more effectively, focusing on interventions that target the most influential factors. This could involve implementing attendance monitoring systems, providing additional support for students with low attendance, or developing programs that encourage regular class participation. Moreover, linear regression analysis can be instrumental in optimizing resource allocation and strategic planning within the university. By predicting future trends and outcomes, administrators can make informed decisions about budgeting, course offering, and faculty hiring. For instance, linear regression models can forecast enrollment numbers based on demographic trends, economic indicators, and historical data. This allows universities to plan for future demand, ensuring that they have the necessary infrastructure and personnel to accommodate incoming students. Additionally, linear regression can help in evaluating the effectiveness of various educational programs and initiatives, providing a quantitative basis for continuous improvement and innovation. In summary, linear regression analysis serves as a powerful tool for universities to enhance their potential efficiency, improve student outcomes, and make strategic decisions that drive long term success. Decision trees, random forests, and neural networks are powerful machine learning techniques that can significantly enhance university systems by providing robust predictive analytics and decision making capabilities. Decision trees are intuitive models that split data into subsets based on the values of input features, creating a tree like structure of decisions. Each branch represents a decision rule, and each leaf node represents an outcome. For universities, decision trees can be used to classify students into different risk categories based on their academic performance, attendance, and engagement metrics. This allows for targeted interventions and support programs, ensuring that at risk students receive the help they need to succeed. Random forests build on concept of decision trees by combining multiple trees to create a more accurate and reliable model. By aggregating the predictions of numerous decision trees, random forests reduce the risks of overfitting and improve the model's generalizability in a university setting. Random forests can be employed to predict students' retention rates, identify factors that contribute to academic success, and optimize resource allocation. For example, a random forest model might analyze a diverse set of features, including student demographics, financial aid status, and extracurricular involvement, to predict which students are most likely to drop out. This information can guide proactive retention strategies such as personalized counseling and financial support, ultimately enhancing students' retention and graduation rates. Neural networks inspired by the structure of and function of the human brain offer a sophisticated approach to predictive modeling in a university system composed of interconnected layers of nodes, neurons. Neural networks can capture complex nonlinear relationships in the data. This makes them particularly effective for tasks such as predicting student performance, identifying learning patterns, and optimizing course recommendations. For instance, a neural network model could analyze student interaction data such as online course participation and assignment submissions to predict final grades and identify students who may need additional support. Additionally, neural networks can be used to personalize learning paths by recommending courses and resources tailored to each student's strengths and weakness. By leveraging the advanced capabilities of neural networks, universities can create a more adaptive and personalized education experience, ultimately fostering better academic outcomes for the student satisfaction. Whereas in the time series analysis, ARIMA, which is technically autoregressive integrated moving average, and SARIMA, which is seasonal ARIMA, are powerful time series forecasting models that can significantly benefit university systems by predicting trends and patterns over time. ARIMA models are particularly useful for analyzing and forecasting data that exhibits temporal dependencies such as student enrollment rates, financial aid disbursements, and resource utilization. By decomposing the time series data into its autoregressive integrated and moving average components, ARIMA models can capture the underlying trends, seasonality, and random fluctuations. This enables universities to make informed decisions about future resource allocation, budget planning, and strategic initiatives. For example, ARIMA models can forecast enrollment trends, helping administrators plan for the future class size, faculty hiring, and infrastructure needs. SARIMA extends the capabilities of ARIMA by incorporating seasonal components, making it ideal for data and exhibits recurring patterns at regular intervals. In the university setting, SARIMA model can be used to predict seasonal variations in student behavior, such as peaks in library usage, or the students who are using the library during exam periods, or fluctuations in campus dining hall attendance. By accounting for the seasonal effects, SARIMA models provide more accurate and reliable forecasts, permitting universities to optimize their operations and services. For instance, SARIMA can help predict the demand of student housing during different semesters, enable better management of residential facilities, and ensuring that housing needs are met effectively. Overall, ARIMA and SARIMA models offer valuable tools for universities to anticipate future trends, optimize resource planning, and enhance the overall educational experience for students. Now let's look into clustering algorithms. K-means clustering and hierarchical clustering are essential unsupervised learning techniques that can significantly enhance university systems by identifying natural groupings within the data. K-means clustering is a positioning method that divides data into predefined numbers of clusters, K based on the similarity of the data points. In a university setting, K-means can be used to segment students into distinct groups based on their academic performance, engagement levels, and demographic characteristics. This segmentation allows for targeted interventions and personalized support programs, ensuring that each student receives the resources and attention they need to succeed. For example, K-means clustering can identify students who are at risk of academic failure, enabling early intervention strategies such as tutoring and mentorship programs. Hierarchical clustering, on the other hand, builds a tree-like structure of clusters, known as dendrograms. By recursively merging or splitting clusters based on their similarity, this method does not require a number of clusters to be specialized or specified in advance, making it a flexible and exploratory tool. In a university context, hierarchical clustering can be used to analyze and understand the relationships between different academic programs, research interests, and student cohorts. For instance, hierarchical clustering can reveal how various departments and disciplines are interconnected, technically facilitating interdisciplinary collaboration and resource sharing. Additionally, it can help identify subgroups within the student population that share common characteristics or needs, permitting for more tailored and effective educational strategies. By leveraging K-means and hierarchical clustering, universities can gain deeper insights into their data, optimize resource allocation, and create more personalized and supportive educational environment for all students. Predicting student retention. Objective is identify students at risk of dropping out. The data uses academic performance, attendance records, demographic information. The model is logistic regression and decision trees. The outcome is early intervention strategies for at-risk students. So here I have used the AI lecture Colab that I started creating in the previous lecture. So I will actually go ahead and explain this in a moment that how I did that. And again, optimizing financial aid is another area where allocate financial aid effectively to maximize student success. Data use financial aid applications, academic performance, and family income. The model is linear regression and neural networks. In this case, outcome is improved financial aid distribution and higher student retention. Enhancing alumni engagement. Objective is predict alumni donor behavior, how the people who have graduated from the university are contributing towards the university in terms of monetary aid. The data used is alumni engagement history, donation records, demographic information. The model is clustering and random forests. The outcome is targeted fundraising campaigns and increased donations. Implementation challenges, the data privacy, model interpretability, scalability, bias, and fairness comes pretty handy. Let's look into this with one example each. Data privacy is a critical concern in the implementation of AI within the university system, as it involves handling sensitive information about students, faculty, and staff. The integration of AI technologies such as predictive modeling and personalized learning platforms necessitates an it also brings in the collection and analysis of vast amounts of data. This data can include academic records, financial information, health records, personal identifiers, all of which are subject to stringent privacy regulations and ethical considerations. Universities must ensure that AI systems are designed with privacy by default, incorporating robust data protection measures from the outset. This includes implementing encryption, access controls, and anonymization techniques to safeguard sensitive information and prevent the unauthorized access. To address data privacy challenges, universities can adopt several best practices. Firstly, obtaining informed consent from students and staff is essential. Clear and transparent communication about how data will be collected, used, and protected can build trust and ensure compliance with privacy laws. Additionally, universities could conduct regular privacy impact assessments to identify and mitigate potential risks associated with AI implementation. This involves evaluating the data collection process, storage practices, and sharing protocols to ensure they align with privacy standards. Furthermore, universities can employ differential privacy techniques, which add noise to data to protect individual privacy while still permitting the meaningful analysis. This approach ensures that AI models can drive valuable insights without compromising the privacy of individuals. Moreover, universities must stay abreast of evolving privacy regulations and technological advancements. Laws such as General Data Protection Regulation, which is GDPR in Europe, and the California Consumer Privacy Act, or CCPA, in the United States set strict guidelines for data handling and privacy protection. Compliance with these regulations require ongoing monitoring and adaptation of AI systems. Universities should also invest in training and awareness programs for faculty, staff, and students to promote culture of data privacy and responsible AI use. By prioritizing data privacy, universities can harness the benefits of AI while ensuring the protection and trust of their community, ultimately fostering a secure and ethical educational environment. Model interpretability is a crucial aspect of AI implementation within the university system, as it ensures that the decisions and predictions made by AI models are understandable and trustworthy. In an educational context, AI models are often used to make high-stakes decisions such as predicting student success, allocating resources, and personalizing learning paths. Ensuring that these models are interpretable is essential for building trust among stakeholders, including students, faculty, and administrators. Interpretability allows educators and decision makers to understand the reasoning behind the model outputs, validate its accuracy, and identify any potential biases or errors. This transparency is particularly important in sensitive areas like student admissions, financial aid distribution, and academic interventions where consequences of misinterpreted or biased predictions can be significant. Fostering a culture of interpretability and transparency within a university system is essential. This includes training faculty, staff, and students on the importance of model interpretability and providing them with the tools and knowledge to critically evaluate AI models. Universities can also establish governance framework that prioritize interpretability, accountability, and ethical considerations in AI implementation. By integrating interpretability into the AI development and deployment processes, universities can ensure that their models are not only accurate but also fair, transparent, and trustworthy. This approach enhances the overall effectiveness and ethical integrity of AI driven decisions, ultimately benefiting the entire university community. The data governance, continuous monitoring, stakeholder engagement, and ethical considerations. Since I have discussed on all of these topics in quite depth in the previous examples, so I will leave it for you to conduct a research on your own that how AI implementation within an organization should be done according to your research. And these are the best practices I thought to share with you. Here is a predictive analytics lab I have created where I imported the pandas, the scikit-learn or sklearn, and I also added the example data in it, which has the GPA, attendance and retention, and then 1 means retained, 0 means dropped out if the course was taken and that happened. And then I have created a data frame by using the pd.dataframe data. Then I have created the features as a target. So the X is GPA and attendance, and Y is the retention. And then I applied the standard linear regression to split the data. And when I go further into this, I initialize and train the model of logistic regression because I have opted for the libraries, and then I did fit the model on top of that, and I created a Y prediction. So I set print accuracy and with the accuracy score as well as classification report. So it has created a precision recall F1 score and support. I suggest you to look at the precision recall F1 score and support in your readings. You can find these in Google Scholar or IEEE Explore in depth, that how people have used that. So I have put the example prediction for a new student, the new student from the data frame, where GPA is 3.3 and attendance is 88%, or the prediction model, when it predicts, it says print the prediction for new student retained or dropped out. When I have trained the model, it has given me the answer. Prediction for new student means retained, would not be leaving the university or the semester. So unsupervised learning involves training algorithms on data that has no labeled responses. We have discussed in the previous lecture in quite depth, so I suggest you to revisit the lecture 1. And useful for exploratory data analysis, identifying hidden patterns and data pre-processing. Unsupervised learning is quite helpful in that area as well. Clustering is the task of dividing a set of objects into groups, clusters, as discussed earlier, so that objects in the same group are more similar to each other than to those in the groups. So applications in market segmentation. So the new parents buying the children products, the older adults buying the the products which are used for their everyday use, can be cleansing and all that jazz. Image compression. So if there is a big image, when you express it, does it lose integrity? Anomaly detection. If I'm using a credit card for my standard Walmart, Target, or Home Depot or Lowe's, then if I suddenly go and someone uses my card in Norway, Bergen, Norway, then that's an anomalous character. I am not in Bergen, Norway as per my last transaction. That's the anomaly. Recommendation systems. Netflix and Amazon Prime use the recommendation systems, and they are based on the clustering, so I thought to share that with you also. Types of clustering, as we discussed, the k-means and hierarchical. So the partitioning methods are used in k-means clustering and k-medoids. I suggest you to look into that in your readings. Conduct a research on that. Hierarchical methods are agglomerative and divisive, so I suggest you look into that also at Google Scholar or IEEE Explore. Density-based methods are dbScan, optics, and model-based methods are Gaussian mixture models or GMM. I would suggest you to conduct a research on these types of clustering so you understand what other people have done. Google Scholar is the best bet that you can find, or the university library system if you're studying in a university, at the time when you're looking at this lecture, or at this very moment if you're studying in a university and you're looking at this lecture, so you can look at that. K-means clustering I have discussed quite in depth. I will just share with you that a little bit more tidbits here. The algorithm is initialize cluster centroids, assign each data point to the nearest centroid, Recalculate centroids based on the assigned points. Repeat step 2 and 3 until convergence happens. The strengths are it's simple, efficient for large data sets. The weaknesses are sensitive to initial centroid placement, assumes spherical clusters. So I would suggest you conduct a little research on k-means clustering. What is a centroid and how you work with it. Here's a little example. Let me share that with you so you understand it in more depth. Imagine you have a data set of student exam scores in math and science. You want to group the students into 3 clusters based on their performance. Initially, you randomly place 3 centroids in the score space. Then you assign each student to the nearest centroid based on their scores. After assigning all students, you recalculate the centroid as the average score of student in each cluster. You repeat this process until the centroids stabilize. At the end, you have 3 distinct groups of students, each represented by a centroid that reflects the average performance of the students in that group. This helps in understanding the different performance levels among the students. Hopefully this is helpful. Hierarchical clustering, as we discussed earlier, let me go a little bit in more depth. Start with each data point as its own cluster. Merge the closest pair of clusters. Repeat until all points are in a single cluster. The divisive clustering is start with all data points in one cluster. Split the cluster into smaller clusters. Repeat until each data point is in its own cluster. Strengths are does not require the number of clusters to be specified, produces a dendrogram. Weakness is computationally intensive, not scalable for large data sets. That's why we stay away most of the time from hierarchical clustering. DBSCAN, the algorithm is define a radius and minimum number of points. Identify core points with at least a minimum points number or min points within the EPS or the radius. Form clusters by connecting core points with their reachable points. Points not in any cluster are considered noise. So you remove the noise in that, in the DBSCAN. Strengths can find arbitrarily shaped clusters robust to noise. Weakness is sensitive to parameters or parameter settings, not suitable for high dimensional data. The Gaussian mixture models, or GMM, assume data is generated from a mixture of several Gaussian distributions. Use expectation maximization, or EM algorithm, to fit the model. Assign each data point to the most likely Gaussian distribution. So I suggest you to please read the GMM in Google Scholar. There will be several papers available for you to download and read how people have used a DBSCAN or GMM. The strengths for GMM are can model clusters within different shapes and sizes, provide probabilistic assignments. Weakness is computationally intensive and sensitive to initialization. Evaluating cluster results. Internal evaluation, silhouette score, Davies Boulding index. I'm not going to elaborate what these things are because there are some things which you have to conduct research on your own to understand exactly how people have utilized. Once again, IEEE Explore, University Library, or Google Scholar is your best friend here. External evaluation happens at just random index, ARI, normalized mutual information, or NMI. Visualization happens in terms of scatter plots, dendrograms, or silhouette plots. So that's the best bet. I suggest you, I'm leaving some things open for your understanding to go to the next level when you will start conducting a little research on your own. Customer segmentation. Objective here is group customers based on purchasing behavior. Data use customer demographics, purchase history, engagement matrix. Model is k-mean clustering. Outcome is identified distinct customer segments for targeted marketing. So if it's a sports person who's going in, might be buying a bike, might be buying the water bottle, might be buying the socks and the shoes and the dress to do the biking. And then there might be another customer altogether who is into the uh, auto mechanic as a hobby, would go and spend time in Target or in Walmart or in Sam's Club or in Lowe's, in the area where the automotive uh, equipment is available. Image segmentation: the segment an image into meaningful regions. Data use pixel intensity values, spatial coordinates. I suggest you to look into DBScan and find the usage of DBScan uh, in your area of interest and how it can help you in conducting image segmentation for you. Identified objects and background in the image. When you take a picture, it has object which is in the front and there is a background. How that interprets, that is done by DBScan. Recommendation engine. Engines are systems that predict user preferences and suggest relevant items. Importance is improve user engagement, increases sales, and enhance user satisfaction. Application is e-commerce, streaming services like Amazon Prime, the Hulu, the Disneys, and the Netflix of our time at this moment. Social media is like Facebook, Instagram, or TikTok, or something like that. The news websites like CNN, Fox, and ABC or CNBC. Types of recommendation engines: there is collaborative filtering that is applied to get user based or item based. Content based filtering is user profiles, item profiles. Hybrid methods, combination of collaborative and content based filtering. And context aware recommendation incorporates contextual information, time, and location. Collaborative filtering. Let's jump into that a little bit in more depth. User-based collaborative filtering technically recommend use for recommendation of items that similar users have liked. Uses user similarity matrix. So it's a possibility I'm into pickleball and my son is into pickleball. So when we both go into shopping, the recommendation coming in for both of us to buy some pickleball paddles or related gear. Item-based collaborative filtering recommends items similar to those a user has liked. Uses item similarity matrix. So it's a different than user similarity matrix. The strengths are simple, effective for large data sets. The weakness is cold start problem, scalability issues. So we use this on a cache level rather than in depth. Content-based filtering has an algorithm is create user and item profiles based on the features, recommend items with features similar to those of users has liked. The strengths are no cold start problem, can recommend new items. Weakness is limited to item features, may overlook user preferences. It can be applied in the seasonal also. It's a Christmas season, it's a whole different ball game when you go for shopping. If it is some other season, let's say we are heading to a vacation in summer, that's a whole different ball of purchasing that we do. Hybrid methods combine collaborative and content-based filtering, use weighted average for switching or switching mechanisms. The strengths are mitigates weakness of individual methods, improve recommendation quality. Weakness is complexity, computational overhead increases when we go for the hybrid methods. Context-aware recommendations. The algorithm is incorporate contextual information, time, location, user mood, and the user contextual pre-filtering or post-filtering that is utilized in this. The strengths are provide more relevant recommendations, adapt to changing user needs, Weaknesses requires additional data complexity in modeling. The recommendation engines are essential for personalizing user experiences and driving engagement. The future trends are integration with deep learning and reinforcement learning, real time recommendations, explainable recommendation systems. So, if you have ever used a passport application to park your car, as soon as you go on the passport and you sign in, it is contextually aware and it knows exactly where you're standing. So you have to select that parking zone. When you click it, then since it has your data and it asks you how many minutes or hours you would be parked here, and then it charges accordingly to your card. Thank you so much. Happy learning. I wish you best of health. And I would suggest you to definitely look into Google Scholar. You can look at my Scholar, that's Google Scholar, and then you can type my full name, Atif Fareed Muhammad, PhD, and you will be able to get all my published work there. So you can find even most of these, or even all of these topics are covered in several of my publications till date. See you in the next lecture.